Today we are very pleased to have Cyrus Shahabi from the University of Southern California here to give us a talk on his work in GeoDec enabling of geospatial decision making. Professor Shahabi is currently an associate professor and director of the Information Laboratory at the Computer Science Department. He's also a research area director of NSF's Integrated Media Systems at the University of Southern California. He has his BS and MS and PhDs from University of Southern California, and more than 200 articles, books, and chapters and conference papers in the area of databases, GIS, and multimedia. Current research interests include geospatial and multi-dimensional data analysis. Please join me in welcoming Professor Shahabi to Google.
All right. Thank you very much, Jeff, for the introduction, and thank you all for coming. I know that it's very tough to leave the delicious food in the cafeteria and come over listen to a talk, but I appreciate it. So this is, as Jeff briefly mentioned, there's this center at USC called Integrated Media Systems Center, or IMSC over there. And it's basically a center supported by National Science Foundation for 11 years. It started in '96, so we're kind of towards the end of it. One of the goals of the center is to do multidisciplinary, multi-investigator research. So as an example, what I'm going to talk today about is GeoDec, which stands for Geospatial Decision Making. And this is this project that has basically more than one faculty involved. So as you see, a group of 5 faculty involved. And for some reason, my laser pointer doesn't work. Basically, the main idea is to have faculty from different areas. So we have people from databases, AI, computer graphics, computer vision, and systems collaborating for this project. And if you guys are familiar with the academia, it's usually tough to get a bunch of faculty to work together. So this by itself is an accomplishment, just this first slide, to have all these people agreeing to contribute to the same project and have their names collectively there. Of course, as usual, the real work is done by the staff and the students. So we're just PR to tell you what they did. In one slide, if I want to summarize the vision of GeoDec and the challenges and so on. So the vision is basically we want to be able to build these geospatial spaces. Build these geospatial spaces like a city, both quickly and accurately. So those are very operative keywords here, rapidly, because we basically want to distinguish ourselves from, for example, Hollywood, where they spend a lot of time and a lot of human resources building these 3D virtual environments, and accurately because we want to be able to build things that are basically unlike Google Earth, for example, that the main users are public, that they just want to find houses and stuff. We want to build things that can be used for geospatial decision making, for querying. Therefore, they need to be more accurate. And I will show some examples of cases where we need to do things more accurately than, for example, Google Earth. And then finally, the idea is not just the space, but of course time, and then be able to do querying and access. So if I want to just summarize the challenges we have is to get arrays, is for realistic rendering and accurate information fusion and so on. There are many applications out there. I was talking actually to the Google Earth chief technologist and telling him that I see more and more applications that serious users using Google Earth versus a lot of S3 GIS type products to do real GIS integration and analysis. So examples include city planner, emergency response, military intelligence, simulation and training, and so on. The last item was kind of interesting because when we started the project, we were just showing this to a bunch of folks. And then we see a lot of people from NBC and ABC coming in and showing interest in the project, and we asked them why you're interested, and they said, for example, there's a location like Vatican, and we want to do a quick news in that area, so it would be very nice if we can quickly build a 3D model, we can fly through and do all sorts of information integrated into that environment. So we added that as another application which can benefit from a system like that. This is just to give you the type of data sources that we are looking into integrating for GeoDec. Very much, I guess, similar to the type of things that Google Earth integrates right now. Satellite images, aerial photographs, 3D models, and so on. And the idea is that they all coming from different sources. They are having different formats and different standards and so on. So right now, most of our demos are basically in this blue area, the experience part. However, we are trying to move into this area where you can start asking questions and doing analysis on the data. And by the way, if you have any questions, feel free to interrupt me and ask the question on any of these. This is another block diagram of the system. This is basically showing all the data sources here. And you see some of these data sources directly being used for integration. Some of them, in addition to being used directly, they also go through some computer vision, computer graphic processing. And as a result, we generate new sources of data that, again, they would get integrated. And the final result be displayed to the user for interaction. And I'm going to do a little bit of a change here. Minimize my shortest path. All right. So now let's get to some of the underlying technologies that we have and how they come together for building a system such as the one that I just mentioned. The three specific pieces that I'm going to talk about are building the 3D models, then putting textures on them, and then fusing all sorts of geospatial data. So as I said, this is multidisciplinary project. So the first one, for example, is done by my colleagues in computer vision. So I have a little bit of information about the details. So I tried my best to answer your questions there. But if you have more detailed questions, I might refer you to them. And the second one is by my computer graphic colleagues. And then the last one is the piece that's mainly by myself and my AI colleague. So the first step basically is that you want to build 3D models. I think Google Earth recently acquired SketchUp as a software to build these 3D models. So this is an alternative approach to do that. This project actually started by receiving funding from NGA and went through different phases. So right now it's actually the last phase, and it's kind of ready to become a product. And the idea is to get two images, say stereo images, aerial images of an area, and then by interacting with the image, but minimal interaction with the image, you basically build the 3D model. I think the best the way to show it is through a demo. So I think I can leave this slide somewhere for you guys if you need to see more information. But the system is called IMVS. Let me just quickly show you how it works by quick video. So this is, you start with the 2D image. You work on one image only. You start, the box is automatically generated around the building. Then this is the user clicking on specific points and basically making the, identifying the corner points. The height information is calculated automatically by the software by using the other image. As I said, there are two images, but the user is only interacting with one image. So with some little clicks here and there, you end up with an accurate model. I show you some examples of the model. Here are basically, here are the example of the aerial images that you have. And these are the models that are built using the software as a result. And as you see, you can get into very much details on the model if the application requires such a detail. So for we basically, I'm going to show you a couple of areas that we actually built the model. So for an area in DC that I'm going to show you next, actually, it took half a day. But this is the PhD student who actually built the system. So you're assuming an expert user here. But one of the reasons NGA kind of like this is because at each point in time, you only work with one 2D image as a user. So you don't really need to have any 3D view of anything. Just work with the 2D images. The depths, the heights is calculated automatically by the software by using the parameters of the stereo images. Because you have the image from two angles, you can calculate the heights. So here is the DC area that I'm talking to. These are the Google models. And I assume that the focus there was not accuracy, as I said, because of the application. So there are some areas that I want you to look at. For example, that area up there and these buildings here that are kind of boxes. And these are the models we built in half a day with the software. So you see all the details of the buildings are incorporated into the models. And this is another area we did. This is USC campus. I'm going to show you actually a demo of this one. So, so that was the first step. You end up with these models, but as you see, the models are very dull. These are these white blocks that you can't get a sense of what exactly is the building. So the next step is to apply textures to these models. So this is the part where my computer graphic colleague work, and his basically team looking at different techniques to use both aerial image as well as pictures taken from buildings, and then use that to texture map the models. Some of the challenges he's involved with is, for example, here you see that you can't see the whole building because of the trees. So how you can basically either extrapolate the texture behind the trees, or if you have another picture from a different angle, try to fuse the two and generate these missing textures. So it's basically the one that extrapolate or interpolate is called synthesis. The occlusion detection and removal is the part where you use multiple pictures to basically see what's happening underneath and remove the obstacles. So here is an example of, again, the USC campus that I'm going to show you, where we wanted to texture map this building, and we didn't have the full building in one picture, so we had multiple pictures that were fused. The other piece that my colleague work is not only map the static textures from images, but also mapping textures from video. So that would give this sense of dynamic moving objects to the model. So I have another quick video. And if you think I'm moving the mouse very slowly, make sure that I understand that I'm doing this backwards. Okay. So this is the 3D models with the video textures. The buildings are real 3D models. So as we navigate through things, they stay correct. But the video, like the objects like the map poles or the trees, these are 2D objects. So so as we move around, you see that they actually get bent because there are just 2D frames on top of the 3D model. Some areas like here, for example, you see the cars disappear because we didn't have any video camera for that area, so we just used the texture map from the aerial image and so on. Okay. So the last piece that I'm going to talk about, and this is the longer one, so don't expect this one to finish soon because this is my own work, is the part that you want to now integrate all the other geospatial data you have about that area. So what you get from the first two pieces are basically the models and the textures, but this is only good for navigation. You don't have any real information about the area. If you want to do real geospatial decision making, you need to have information. So there are a bunch of data sets out there, and I'm sure you guys are aware of. So imagery at very good resolution, there are a lot of them. There are many maps of different areas that are around. We can get road network data, power line data, railroad tracks. So a lot of vector data available out there. In our case, for example, we have a database from NGA of the entire world, vector data for the entire world. Elevation data, digital elevation data available also again from NGA. A lot of point data available for around the world. Again, NGA is one source. It was called NEMO before, but that's basically lat and long of points with the description of the point and all sorts of information about it. There are a lot of websites that are not geospatial by nature, but they have geospatially related information. One example is property tax site, where basically it has parcel information. There are online telephone books and railroad schedules where you can find, for example, temporal information as well as spatial information like the stations, the coordinates, the addresses, and so on. A lot of other sources for temporal data like traffic data, GPS data, and video out there. So, and then of course weather information. So the question is that how we can integrate all these different sources, and the idea here is not to do it per application from scratch, but to have certain tools and certain framework so you can do the integration quickly for any given application. So if I want to, for example, focus on an emergency response application and identify these certain sources, the focus of our work is to build tools so you can quickly wrap these different sources and then generate this integrated model so that you can integrate all these data and then start asking questions. So I'll give you a couple of, actually 3 examples of different fusion challenges that we work with specifically. And start with the first one, where is the challenge that I think is very relevant also to Google Map and Google Earth, which is integrating road network data with aerial photographs or aerial images. So if you look at the data here, for example, you see an aerial image and you see the vector data, the red lines. And as you see, the red lines don't match the actual roads on the image. And this is a very typical problem, not because either of these sources are wrong, it's just because the Earth is not flat. So people use different projections or they use different elevation models to fix their data sets. And then as a result, when you put the two on top of each other, they don't align. So this is not just our problem here or examples from other places. Actually, Google is doing pretty well. I don't know where you guys get your vector data, but still it doesn't match correctly, but it's pretty close. But it depends on the area that you look at. I know Microsoft using the same vector data that we're using, which is NAVTEC, and they don't do any correction. So you see, it's actually worse in this case that the road network and the image, they don't match. So what we want to do is basically start from this, which is exactly the road network data from NAVTEC, and then automatically generate the blue one without any human in the loop, so you can fix the error. So you might say why this is important. So as I said, depending on the application. If the application is just for a human to view things, it might be okay if there are some mismatches, for example, like here. However, for example, if you're building a simulation training system and you want, for example, tanks to move on the road, and you have the satellite image or 3D model as the background, the tanks can actually move on vector data, not on the image, because that's the information they have in the simulation. And you don't want the tanks to move over the houses. Sometimes you do, but hopefully you don't. Depending on the application, you may want to have a very accurate fusion. Another example, actually, is if you want to do geocoding. So assume that you have the correct alignment of the vector data to the images, then it would be much easier to identify houses and parcel information. And then this is where I told you that you can integrate this with all the geospatially related sources like Yellow Pages and property tax sites, and so on, to get all sorts of information about public information about the area. So this is actually what is called geocoding. You start from a mailing address, and it's reverse geocoding. You start from a coordinates and get back the mailing address. So what's our approach to do this? So this is just the technical term for this work is called conflation, which is the work that you get two sources of data, in this case, geospatial data, in this case, a satellite image and road vector, and then you go through the process of aligning them correctly. The traditional way of doing this is basically a human basically sit down and say, okay, between these two sources, I find the set of pairs, points that I call control point pairs, that they match with each other. So I know, for example, this intersection here is the same intersection as this one. Okay, so a human basically identify these points, and then you go through the process of, forget about the filtering, but you go through the process of rubber sheeting, which basically align the two sources. The reason that this is called rubber sheeting is because as if one of the sources is on rubber and you move it around, okay, so it matches the other source. And the reason that this is rubber and not steel is because you're dealing with a bunch of local transformations. So the problem is not as if you just take one of the sources and move it to the left or the right and fix it. You need to do a lot of local transformations. So it's not one global transformation, it's a bunch of local transformations, and that's why you need all these control point pairs to identify where you apply the local transformations. So that we just use so that's actually not our contribution. The transformation, we just use a known technique. Okay, the contribution is actually on this part where we replace the first part that I told you that the human sits and identify the control point pairs. We replace that part with our algorithm. Okay, and the way we do it is this. So let me first tell you how this would have been done traditionally. Traditionally, if you want to do this automatically, for example, for the alignment of roads with images, the best feature that you can find for the control point pairs are intersections. Okay, because intersections are easy to identify on vector data, and they're also relatively easy to identify on images. Okay, so if you want to use a pure image recognition technique, you basically use some sort of a machine learning technique like Bayes classifier, and then you classify. You first train it. You basically go. A human goes and say, okay, these pixels are on road, for example, and these pixels are off road. Okay, and then the system learns this and classify things automatically. So after a while, basically any pixel you give to the machine learning technique, it would tell you whether it's on road or off road. Okay, in this case, the white pixels are on road, the black pixels are off road. Okay, now here is the problem. The problem is that if you do only that, you see that area, the black area in the road, even though those are on road pixels, they are colored black. And the reason that they're colored black are because of the tree here, right? That's why they are classified wrong. The other example is this area here over there. You see that there are a bunch of white pixels that are classified on road while they're not really on road. But the reason is this rooftop, it has pretty much the same color and texture as the road, and that's why you misclassify. So no matter what you do, you will end up with this noise. And if this happens and you're just doing a blind intersection detection, there's no way that you can identify this as an intersection from that image, right? Because it's just noisy, all right? Now, what we do, which makes this a little bit easier, is we use the vector information to narrow down our search space, okay? So from the vector data, we know that there's already an intersection. We know that it's not exactly there, but we know that it's in an area around it, okay? So first of all, we only need to search that area for intersection, not the entire image. More than that, we know that there are two lines, for example, on this intersection. And also from the metadata about the vector, we can sometimes know even how wide these roads are. So we basically generate a template of what we're looking for. And then, now that we have exactly the template that we are looking for and the area that we are looking for, there's a better chance that we actually match it and identify it as an intersection. So that's the piece that basically the main contribution from our side is to do the control point pair detection. However, no matter how well you do things, you will end up with wrong noisy points. So here is an example where you first find the intersection on vector data, the red points, which is kind of easy. And then using the technique that I told you, we find the corresponding intersection points on the images. So as you see, you still end up with wrong intersections. So for example, this one here, right? This is a wrong one detected. So no matter how well you do, you still end up with those. But another advantage of our technique is that you don't really need to find all intersection points. You need to only find a certain number of good points. So we use, again, a known filtering technique, which basically look at the displacement of the intersections and then find a median vector and throw out all the outliers. So as a result of that, we end up throwing out this one, for example, because it's an outlier as compared to the other vectors. Okay, so, okay. Now after we find those intersection point pairs that we know for sure they are correct, then this is the part again that we are just using a known grouper-fitting algorithm, okay, which is the Delaunay triangulation. So we basically from those points generate the triangles, and then use the vertices of the triangle to generate the transformation matrix, and then multiply the transformation matrix to the entire triangle. Okay, so that's the way that the transformation works. So here are some results. We did a project for USGS to align their data set automatically. We first started with tiger data, which is pretty bad. So the red one, tiger data, is really bad quality vector data. And we did some fixing there. Here is NAVTEC data. Oh, I don't have any more. But if you're interested in the actual quantification of our technique, and we did lots of experiments to compare how well we did on different areas. So I can send you papers and if you're interested. The second problem now that I'm going to talk about is not only overlaying vector data with images, but also maps with images. Okay. Now here we have two problems. One problem is that maps are raster data; they are not vector data. So you need to basically align raster with raster. The other problem is that we do not assume that we have the corner points, the coordinates of the corner points of maps. Okay. So this is the reason for this is that a lot of maps that you get from the web, for example, you don't know the coordinates. You know generally the area, but you don't know exactly what are the coordinates of the map. So here is our approach basically for this problem. We basically start with the map. We have a lot of, I will talk about that, map processing techniques where we identify the intersection on the roads on the map. And the same technique that I just described for the vector data, we use that same technique to find the intersection points on the image. Okay? So now what you have is a bunch of points here and a bunch of points here. You know that this map relates to this image, but you don't know exactly where. Okay? Here is where we basically observe that there is a pattern to the intersections of a map that you can kind of use it as a fingerprint of that map. And by doing the pattern matching between this set of points and this set of points, we can identify the area of the map that matches with the image. So let me show you a little bit of a, if you're interested, again, I can tell you more about the techniques we use for the map intersection detection, but that by itself is a challenge because a lot of maps are very complicated. They have all sorts of background layers. They have text in the middle of the roads and so on. So we need to identify all these layers and then isolate the vector layer and then find the intersections on the vector layer. So that's by itself is challenging. But once we do that, then we use our point pattern matching algorithm that basically identify the match of this set of points on that set of points. And here we are not doing a blind kind of point pattern matching. We do exploit the geospace because we know, for example, the directions and certain orientation, and we use that information to reduce our search space to find the pattern. And then again, we do the same approach as before for the rubber sheeting algorithm, we do the triangulation and the transformation. Now, the last phase, which is a little different from vector data, is that we, in order to overlay this one on this one, we basically do what computer graphics folks do as texture mapping. So we take that triangle and texture map it on its corresponding triangle. And we can do it either way. So you can either use the map as the source, or you can use the image as the source. So the result would be something like this, where you have the map on top of the image. You might say that why this is important. I give you a couple of example applications. One is that for a lot of areas in the world, we have aerial images and we have maps, but we don't have anything else. So by doing something like this, basically you label the roads on the image with the information on the map. The other use for this is, for example, for an area here, from the map, you know that there's a park. So if you just have the map, you know that that's a park. If you want to, for example, land a helicopter, you want to make sure that there's an open space in this park. And that's not given to you by the map. But once you put it on top of the image, now you know that here is a park and there is an open space in this area, for example. So the combination of the map and image give you much more information than each one of them separately. Another example that we did actually for the DC area was to align metro and bus maps of DC on the satellite image. So here, for example, you get the very detailed information of the relationship between metro lines and houses, for example. For emergency response type application, this is very important. And you see that the metro lines, in our case, there are all these jagged lines and curvy lines. And the reason that usually metro lines are straight lines. So because of our alignment process, we ended up to deform them in order to match to the roads. Okay, I think I have time to go through my last example as well. So this last one is just an example of an integration of sources with both spatial and temporal information. So here we have three sources. We have a source public website that has the information about different railroad stations and their addresses from which we can do geocoding and get the coordinates. We have railroads information, the actual vector data of the railroads, and we have the schedule of the trains leaving, for example, one station arriving the other station. So from these three sources separately, you can ask certain questions, but you can never, for example, ask that I want to know all the trains that would be in this area for a given time frame. Okay? None of these sources by themselves alone can answer this question. But once you integrate the three sources together, and that's what we did basically, then you can start asking questions that basically range queries on space and time. So you identify a time interval and space, and you ask for all the trains, for example, that would be in that area. And the system now can answer this sort of question. So this is just another example of the power of integrating multiple sources together. So for this demo that I'm going to show you now, we use all these techniques that I described. So we built the models, we put the textures. We also conflated both vector data as well as raster maps. The maps are from the tram routes on the USC campus that we didn't have them in vector information. And we also did some temporal data. We did tracking of the trams that they get updated every 10 seconds. And we put that information on top of the models as well. So just a quick summary of what we did throughout the past year. So the project started officially kind of like in April 2005. Our first demo in June 2005 for NSF was that Washington, D.C. demo that I showed you with the video of the cars moving and so on. And we had a separate demo that shows the integration of sources. That was the metro map. By 2005, for the USC 125th anniversary, we did a modeling of the whole USC campus and integrated everything together, as well as adding the live video, live GPS, and also a gesture-based user interface for coolness factor. And then I'm going to show you this one as well, where by May we did a Another demo for an area in downtown LA. We did our own 3D models and live streams of the video. In addition to that, we also generated a Google Earth version of it, and I'm going to show you that one as well. This one only has our 3D models, but they're very accurate models. So the project was that they want to, this area here, they want to get rid of these two buildings and get bids for putting a new park in that area. And at the beginning, and this is supported by ALA Times, so at the beginning they just want to put some pictures of the area on the web. And what we suggested is instead of the pictures, put something like this so that people can navigate. And also, in addition to that, put Google Earth with all sources of data that I'm going to show you later that we added to it so that people get much better view of the area that they want to change. So the yellow area is the area, and these are the two buildings. So we did a little bit of special effect for them too, so that they can. As you see, this one was pretty accurate. We even had the train information and some very tough buildings. Now let me show you the USC campus demo. So this is we started from the aerial image. We did correct the vector data, the techniques that I described for you. So here is the vector data now exactly on the 3D model at the right place after correction. As you go close, zoom into the model, this is the tram road. So as you see, the original map was actually not correct spatially, but then once we put it on the rows, you see all the curvy lines that is the result of the conflation. As you zoom in to the buildings, here is a query system that actually goes to our mediator, to information mediator, and get information about the building. So the name of the buildings are not hard-coded. They are actually queried to another source that gets the name of the buildings, and they pop up. This is the video texturing. If you come to my lab and see this demo, my lab is actually in that building, and these are live video cameras. So if you go from the window, you can see the same view as what we showed during the demo. Right now, we have much better textures on these buildings, so the new demo looks much more real. But the models are the same models, just that we did a better texturing. Here is the gesture-based user interface, so you can actually control the system with gloves. Kind of a Tom Cruise fashion. And those are the blue things are the trams, so their location get updated. So right now we are working on a query that hopefully should be ready in 2 weeks for the NSF site visit, where you ask questions about the trams and their trajectories and then see the corresponding video. Live on the edge here and show Google demo to Google folks. And this should be fast here, right? The servers should be running. Or actually, you know what? Maybe for this one. It's not in the building. No, this is me. I just want to have my own display as well. It's much easier to control things. Okay, so let me first show you the USC campus. So this is now the same tram map. We aligned it with the Google Earth. So that's actually what at some point Mark suggested us to do. So you basically get the same tram route information overlaid on Google Earth as well. And now I have a couple of queries that we're working on right now. So one is, let me first show you the stations. So these are the 4 stations. Okay, let me first show the trams and see if it works or not. Okay, here we go. So this is now the live location of USC trams. So we have an XML file that gets updated, and we read it and generate these KML files that gets refreshed. So you see that the tram, for example, moving over there. So this is the real location of USC tram right now. And one type of query we're thinking is that if you have the stations, then let's say that you have station 1. These are tram stations, and station 2. Let me turn on a couple of stations here, 3 and 4. Okay. Now, if I go and want to know, for example, here, what is the closest tram? So we kind of enhance Google so you can ask queries. The result of the query and I don't know why this actually moved to a totally different area, but probably I did something wrong. But it's trying to, oh, I know. Let me go back to USC campus. There we go. So that was the result of the query, the green thingy. So I did a little bit of too much movement. But the green thing is the closest tram to station 4 at the time of the query. Of course, things changed. I guess this is not the closest. Now this guy is closest. So if I do, let me turn it off and do the query again. Oh, man. You know what? Just do it here. Oh, I did it to station 1. So the closest tram to station 1 is this guy. Okay. Another query is if we want to just track all the trams closest to station 4. So basically, this is now tracking. So it's not only at the time of query, but it basically keeps tracking the tram closest to station 4. So if at some point the tram changes, it would change we can do the same thing for like station 2. So this is now the closest tram to station 2. All right. Turn all these off. And go to the downtown area. So now we're going to downtown LA area for the same area that they were planning to do the bidding. I don't have time, but you guys can go on. The KML file is on my website. You can go and play with it. But basically, we show the buildings, the 3D model of buildings, both our buildings and Google Earth buildings. So you can do a comparison. If you turn the Google Earth buildings off, you see our building. So for example, this area here, you see the details of our building versus Google Earth building. Actually, there are certain areas that Google, I think, built a model from the older imagery. So there are certain areas that Google doesn't have a building and we do have a building. Here is the parcel. So the red lines that you see are the aligned parcel data that we aligned it with the imagery. And if you can click on it and ask questions. So for example, here you can say, I want to compute. So this gives you all the information about the parcel. If you click on compute, basically send a query to our mediator that hopefully will come back at some point. And OK, here we go. So it comes back with an XML file that has the actual calculation of the area of that parcel. And there are all sorts of other queries that you can do on a parcel. So for example, you can ask for the nearby parks. So if I say find, it basically tries to find the nearby parks. And the reason it's taking time is because every one of these clicks actually goes back to our mediator, submit a query, and get the result back. OK, so if you're interested, I have lots of KML files that we did a lot of querying. But just let me finish with this slide, which basically shows where we are. So right now, this is the current state of the system. Up there, we have 3 different user interfaces. I already showed you AVE. That was the video that I showed you that has video texture mapping. Google Earth, I also showed you. And Nega is one that we are working right now and can do a lot of query and interaction with the models. So all of these are basically built on top of this thin middleware called Julia, where it basically has different blades for each user interface that we add, but then sends a unified querying to our spatial databases, to our mediator, or to our video server. And then basically this would generate new queries to all these other sources, and the result goes back. I think one of the main problems that we are dealing with, which I think is similar to the type of things that Google Earth might be looking at, is that if you look at the problem very abstractly, we have real-world data, terabytes of it down here, and we have limited pixel space up there. And the question is that how to go from here to there efficiently. And right now, there are 2 different approaches that, for example, most of the web-based systems use this approach, where they build each frame at the storage and send it out. Or the GIS products, which is the other way around. They actually send everything to the client, and the client decides what to show and what not to show. And we think that there is a middleware. There's a hybrid between these 2. So we are, this is our main kind of research problem that we are looking into. And this is my last slide on the different funding we get from different places for this project and some of the prospects. OK, thank you.